Yes, good morning. Very happy to be here and honored to give this keynote talk. I was already thinking this is a student seminar. This looked like a bigger than that. This is good because the topic is really a very, very important one, a very, very big one. And obviously will require a collective wisdom of everybody interested in energy to understand this, explain this, and see how this is going to potentially impact our energy future. So just the $140 million grant is not actually on this topic. It's on the wide bandgap semiconductor, so which is related to this topic, which I will get into a little bit today. So I would like to just try to say if we can take away from this talk why everybody's talking about the energy internet or internet of energy. I'm not a linguist. Try to explain what's the difference between these two. There are people debating about which one, but this has been the name we are using for the last 7 years. So I think as your vice president mentioned, that energy is a global issue. And when we put forward this concept, why we need to develop an energy internet, we were looking at basically the overall global energy demand and the pace that renewable energy or new energy technology are introduced into the market is at a relatively slow pace. Although this picture is a little bit old, this was almost 7 years ago. But still, this picture is still more or less the same, I think, because our business model has now really changed. It's basically we have an incremental improvement in the technology. The insertion pace is slow, much behind than the growth of the population and the per capita demand for the energy use. So I think one key thing industry thought leaders and economists have all agreed that one major issue maybe in the energy sector has been a lack of an industry paradigm shift, and because of that, a lack of innovation and open innovation in this space. We come to that. This is basically the core concept of why we want to look at energy internet as one of the key technology for the future, is to create this paradigm shift in the industry, which will induce the industry innovation. So what do we mean by paradigm shift? So one example, again, this was 7 years ago. This picture didn't change for 7 years. This was what I used 7 years ago when I went to government to say we need a major funding to look at smart grid from a very different angle. Because at that time, smart grid was just beginning, even in the USA, to talk about smart grid, to put some smart sensors and AMI infrastructure into the infrastructure. But that, to us, is just the beginning of what a major shift we think we would need. One major paradigm shift in the information technology area or compute ICT area, of course, is the shift from the mainframe to the distributed computing. Characterized by all these major characteristic is showing here, is ownership, ubiquitous ownership, and the sharing of the information. So we need to remember these two major characteristics of what it really make internet an internet. Internet is not just about connecting information, but it's really about this kind of capability. But this kind of capability, of course, happened in the last 20 years. Originally, we have this mainframe centralized concept and moving towards this distributed information sharing paradigm. So this is really a paradigm shift. And this paradigm shift really result in a major innovation and boom of the industry, and with new business and new job and new economic growth and better standard of living. As we all know, everybody has a distributed computer, 5 of them maybe in everybody's possession. You have cell phone, you have iPad, you have everything. And then you have a new business model. A new business model is not necessarily envisioned or understood at the beginning of this paradigm shift, but it happened as a result of this organic open innovation system. Open standard, equal competition, equal sharing. So nobody is bigger than others. Actually, smaller ones even play better in this new type of in this new IT industry. So today we can add even more, and this happened. Some of this happened in the last few years. For example, Uber is the internet taxi driver. So it's your own taxi driver. So these are all basically so you can see the paradigm shift resulted in economic growth is where what we think we need in the energy area. So the characteristic is shown here, but the one thing we want to say is what is the key enabling technology, right? So we are all engineers, at least many of us are here. You also need to look at what are the key moments in the history that many years ago has to be put down on the ground and make it happen. Of course, that is the connectivity and the open source standard supporting the internet industry. So I think this one you can think internet to this part of the economy is enabling ingredient or enabling technology. So I look at this, internet itself is not the product to some degree. You can think this is like enabling highway, enabling technology make all this happens. So for the energy area, the question is, can we today put down an infrastructure like we did several decades ago for the energy, for the information economy? So that's what I think we think we need. Again, in order to make that happen, we have to look at the characteristic of the energy internet is this. And these are, I think today's power grid or any energy infrastructure, I think we can think we probably, everybody use energy, but we hardly have any of the other three characteristics currently true, is not true. So to make this happen is really a gigantic, there is a gigantic gap to get to this level. So, but again, this might be too simplistic to say the centralized power generation distribution model will immediately move to this. But at least we can foresee if we believe this is where we need in the industry innovation and economic growth, then we will need enabling technology or the infrastructure, maybe it's a better word, that we can call this is energy internet to facilitate these characteristics. And therefore in our industry, then we can see similar booming as a major economic engine. So to the government leaders and government officials, of course, this is very, very important is to look at what is the engine that brings the society moving forward. If the ICT and other technology has done its share, can the energy as a major need for the human society be the engine of the economy as well? So again, then what are the other potential new company can come in here, be that innovator and leader? So this is basically the concept. But so therefore, we define the energy internet as a key enabling technology to facilitate the ubiquitous ownership and sharing and use of energy and sale of the energy. So this requirement is quite high for every one of us to have this kind of capability. As the same way as we share information, we generate information we share instantly with everyone. And so this is basically the major motivation. Many years ago, we put together a team to look at this issue. And therefore, if this is realized, then the energy market, of course, will see a major change. And one question will be, if today's utility company or electricity company are displaced by those millions of generators, and what do they do? Where do they fall in? Where do they make money? So this. If you look at the telecom industry and look at other industry, similar question has been asked. And if you don't adapt, you don't transform, it could be displayed. But if you innovate, you could become the value-added leader again. So what is a value-added leader? For example, okay, in the future, of course, the energy market potentially could transform to a more open. Again, if we all believe this, nobody can really predict the future will 100% be like this. But many people who predict what happened in today's internet really 30 years ago are facing the same challenge when they say something like this. So the market will become more lateral or peer-to-peer or consumer-to-consumer base. And to an extreme, you can almost thinking the electric basically you can say that today's day ahead or hour ahead market could become a real-time electricity market. And you need to have infrastructure supporting that. And utility and owners are all individual owners and company, or it could be organized as a community or as a company side or microgrid. Can all be organized into units, and the unit is you can call that is an energy cell. So the energy cell, of course, this is driven, but this few slide was shown as eventually economics may determine the best practice, because policy could leverage the pricing of the energy to affect human behavior, and so the energy cell will compete for the energy market, and of course, if you don't have any generation, of course, you compete to lower your energy production costs. You buy energy from many competitive suppliers. Then the utility company, of course, has to transform, and they could still provide the generation, because it's not one day we'll reach 100% penetration in distributed generation. But I think the trend is we're going to move into more and more distributed generation for sure. The action is at the edge of the grid, near the customer because of higher efficiency, as well as many of the technology is connected at the low voltage side. Electric vehicle, energy storage, photovoltaic, you name it, electric charging infrastructure. All of this, regardless we believe it or not, is already happening and happening at the low voltage at the edge of the grid, far away from your centralized generation. It's close to the customer. So from a power flow point of view, of course, that is actually good, because we do not have to transport large amount of bulk power across the long distance transmission. But we still need the backbone infrastructure to provide the reliability and the resiliency we need in the grid. That could be potential the value we have to add to, so the big player will still gain significant advantage when we transform into this. One example is, if we look at the telecom industry and other industry, like Google. Why Google is so valuable is because they own you, because they own your information. They know what is your behavior. They know what you do. And same thing could happen to utility company. They need to try to take advantage of this move. If you move to this direction, we're moving into the big data, big cloud computing, electric energy situation. The law company could gain by on the behavior of the customer, then understand what you need, and then develop product and value and deliver to the customer. So at the very end of this energy internet end game is to see this kind of thing happening. So we are just start doing some of the research on what is the business framework we need in the future. And it's very, very rich. Need the electric engineer, need the economist, and need many social science people to get involved to look at this. And again, of course, the barrier is very high. The policy barrier, regulation barrier, very easy to say this is impossible. Nobody is going to agree to do this. But if you talk to the other side of the industry, the people who are currently in the IT industry, they said, if you don't do it, we will come in and do it, which is already happening. Google is developing power generation technology. They're thinking along this line. Okay, so this is 7 years ago. We put all this forward and we developed a center to do the research. And of course, this was accelerated more recently by some much high profile thought leader. One of them is Rifkin, and he wrote a book called Third Industrial Revolution. I think many of you may heard of it. And this has actually generated a lot of impact, much bigger than we professor did. He's an economist. And basically talk about the same thing. And this book now is sold worldwide, particularly in many developing countries at the national level. At the national level, is looking at this very seriously. The third industrial revolution, where the energy internet is one of the key pillars to bring the economy forward, is being identified as a national policy to move forward. So many countries have very seriously look at deregulation policy. One example is China. If you look very carefully, they have issued several government policy to basically deregulate the utility company to allow competition. So this is very big in a sense in terms of the market size and the impact. So to summarize, basically, what is really the energy internet? Again, just to come back to that thing, Elisha said there are the characteristics. I think the characteristic many people think is the internet, the way of thinking about things in the internet world is very different from our electric energy sector. So basically, in the internet world, of course, you can think that the key is the customer is the king, and the product and service must be designed and change, adapt to suit their needs. And same thing can be said about our energy needs. Of course, this energy can go beyond electric energy. Here, maybe we talk a little bit more electric energy centric, but it doesn't have to be. This could include the thermal and gas and other aspect as well, although electric energy is the most flexible form of energy for delivery and management. So it probably will be the first to be impacted by this. And also the overall energy consumption, electric energy the percentage is moving higher and higher. Of course, the second characteristic is the sharing the resources. Sharing resources is the key to reduce the cost. And because utility industry is basically famous for very low asset utilization. And a system is designed for very large margin for the benefit of the reliability. But I think technology can help us to increase the utilization, moving toward a totally resilient system. And again, the large penetration in the distributed generation with a lot mix of technology and very large amount of intelligence, software, and control will help us to achieve that. So this concept actually is already, as I mentioned, is already true in several areas. And the national leader look at this as a major benefit for their country, for their economy. They're hiring a lot of people. They generate a lot of GDP. So whether you like it or not, for example, the banking is 100, 200, how many 100 years industry. And they probably are facing some challenge as well, because a new player can come in with a couple of kids and could threaten them. My children are heavily using this technology now, which basically instant pay the people sitting next to you. This is, we even go what PayPal is doing. Taxi, I can order a taxi here even in Helsinki. Again, of course, there are some issues. There are a lot of protests and strike from the taxi driver industry. But it's happening. You just need to reach consensus how to move forward. Another major example, of course, the retail market is also being major upheaval come from this company, Alibaba. He has a portal called Taobao. That's where basically millions and millions of retailers and get online and sell. So this is basically internet thinking married with traditional industry can create magics. That's basically that third industrial revolution book was basically kind of allude to, and also same thing as what I said. So come back to our traditional electrical energy industry. Therefore, energy internet must support an open, distributed, flat architecture, and has to be software driven. So therefore, there is a lot of, again, this is favor a lot of people who work in the software industry to come into play. And if you look at the architecture, of course, our electric energy infrastructure has a very, very heavy investment in the physical layer. This is one of the issues people cite. There is no way you can do it because we have such a high capital investment in this area. And it's very difficult to manage it, to operate, reliability. So I think that's also, that is true. But I think one thing about an internet economy is to move from high capital investment in infrastructure to light or low cap industry. So this is, again, it's about asset utilization and basically reduce the marginal price of generating the next kilowatt hour. So today, basically, and Amazon is an example. You buy a Kindle, the next book you pay is 99 cents, almost free. So the marginal pricing of getting literature is getting lower and lower. Your initial investment is just a $90 Kindle. That could very soon be given away as a free product. Computer industry is also almost like that. The computer is almost given to you for free now these days. So it's a couple $100. I think even in our renewable energy industry, this could happen too. I think, for example, solar pricing initially many years ago was $60 per watt when it was just starting. Today it's 60 cents and per watt. We're talking about the panel. So this trend will continue. Will only continue if we have more innovation in this industry. It will be given away for free. So the game basically, although I'm actually working in the physical layer, so I hate to say that all this will be given away for free, but technology has a fixed capital cost. Intel processor is a very high-tech product. Nobody can copy and do it. But that cost is keep coming down. They have their own Moore's law governing its price reduction. In our energy industry, by scaling the volume, we can also achieve the cost reduction. So this picture also shows some architecture. If you can see the communication or ICT layer is sitting on top of the physical layer. Of course, on the top is your application layer. So that's where the market and the logistic and the end use will happen. So this picture summarizes one of the architecture discussed by one of the company, totally come from ICT side, are now serious thinking they are also an serious energy player, at least provide service to the energy. They don't want to own all this capital. Their key concept is you don't want to own all those high capital cost assets. You want to operate with very light capital. So of course, this is very, very important. At our group, we have a similar picture, very, very similar. We have a physical layer, and we have an ICT layer we call cyber layer. But the cyber layer, really, if you really break down, it's the same. We will have a communication layer, but communication will be the lower layer. But then you have, very important is this software layer. And this is one area I think is very, very lacking, because internet become internet because they have a very, very standardized open software architecture. Then you have the application layer, which does the energy transaction and economic dispatch. And of course, we need to, from a research point of view, I think this is a major challenge, is how do we study human behavior? Do people really care about saving a few dollars a day on their energy bill? What are the policy and regulation that will have to be introduced to enable this to happen? So it's a very large, complex cyber, physical, social system. So we actually recently wrote a proposal, try to look into more of this layer from a research point of view. So our center's research also talk about, okay, if this is true, what are the key enabling technology missing? And again, we look at the energy information technology area, some key technology develop, standards develop that support that industry, including plug-and-play interface. So we believe that is a very important thing we need to develop for plug-and-play of energy. So to make it easy to connect, distribute generation and storage devices, and so on. An energy router in the information world is literally means your information is transmitted to the intended recipient digitally, and nobody else receives that information. And we need some similar technology, but there is a difference too. In the digital world, digital information is customized to a particular recipient, and you can control that. The energy itself, I think, it does not have to distinguish. We have no way to distinguish the electrons, your electron versus my electron. So this is more a virtual dispatch, economic dispatch problem. So the software, open standard software, and also ability to store information in the information technology is very, very important. In the energy area, so I think we have a lot of holes in all these areas, and this is actually the final applications or allow collaborative energy market. So plug-and-play interface, I think here represented is to define, it's really more about standards, physical standard and communication standard that can unify all the distributed generation and devices. Right now, the industry is moving in many, many directions. So again, there will be a lead later on to how to unify those. And electric vehicle industry is moving one direction. Solar industry is defining their own standards. And storage industry probably going to define their stuff. So that is not good. We need something that can talk to all of them in a universal, open way. So this requires a lot of industry people to come together to do that. And the router, now we need the equivalent technology to be able to route energy. We'll talk a little bit more about that. And software. And here, therefore, another missing link is ability to store electric energy. So we have to add that dimension of degree of freedom for our future grid to improve the resilience. I think it's going to happen. And recently, Tesla already made its introduction. Tesla is not a traditional electric utility company, but they have a big ambition. They say, you don't do it, I do it. They introduced the behind-the-meter installation. Behind the meter. So therefore, I bypass all the regulation issue for a while, at least. Don't worry, once I control all those storage device information. I have a million of those. I have 2 million of those. I have 3 million of those. Guess what? Everybody will talk to them. Because they own the data, they own the information, then they can sit down with everybody because it can aggregate, it's become hundreds megawatt, become 200 megawatt. Very, very powerful, right? So so this is the center I'm talking about. We call our Freedom Center actually, or it's an acronym for this. And for that center was funded with a $40 million government funding over 10 years, plus almost above another $40 million from industry. The center has many industry consortiums. So one way we do the research is organize with a lot of, talk to industry, try to get their buy-in, just like you are doing here. So architecture. I'm coming from a physical world. So first I also want to look at what are the physical architecture we have to do. Remember, energy internet is about infrastructure. So how do we build an infrastructure that can support energy internet applications? So in our center, we also defined an architecture that has at the middle between the medium voltage distribution system and the low voltage side, we're introducing this energy router technology. And energy router is a word I introduced, and everybody's talking about it. They think there is hundreds of millions dollar business in it. To many people, energy router is a software concept. To us, it's both a software and a physical equipment. And showing here, we call solid state transformer. But the solid state transformer with the software and communication capability will behave as an energy router. And utility company in the future should introduce this as a key technology in the grid to interface your main backbone and the customer action. The customer action basically is focused on traditional AC and DC plug-and-play energy cell. And DC, you're going to see more and more DC. And because laterally, many devices are already DCs. Photovoltaic and storage, EV. I mean, basically, almost there is no AC in the modern world. Even variable speed drive convert from AC to DC before become DC to AC again. But of course, this architecture supports both AC and DC system coexistent for a long time. And we also have another technology to improve the resiliency and reliability. It's basically the smart breaker technology. We call it FID. It's a smart breaker technology. So this is kind of like a physical architecture. The point is, if you want to do this 100% penetration and a lot of action by users at the end of the edge of the grid must be reliable and resilient. And so you need to provide an interface to decouple the system parameters of this side to this side. And a solid state transfer has a 4-quadrant control capability, allowing you to separate those quantities. Frequency voltage on this side is decoupled from the low voltage side. And this is just this just shows basically one you can think this is one household, one customer, which one SSD typically can support several households. A larger SSD could support an industry side. The size could be scaled to different sizes. Then you can put many of these together to form a feeder. System with all the software embedded into this equipment, and then and many more of this feeder can form a regional grid. But this will take a while if this is an upgrade of a grid infrastructure, because this is a capital investment like the Kindle book you have to buy. So, and also we don't have this Kindle yet. This is still research stage at the moment. So, but long term also the grid could also migrate further into DC-based system, because this solid state transfer literally eliminates the need to have a traditional AC as an interface, because it will take input either from AC or take input from DC more easily. So we can go directly in the future to building a little bit more DC-based. This is from a physical infrastructure layer point of view. to introduce technology to move into a more resilient and reliable grid infrastructure. And this is possible from a technology point of view. My original background is in semiconductor, so I want to show you this chart. This is possible now to talk about introducing solid-state transfer into electric grid is because there's something else is happening. That's in the semiconductor area. Now we're introducing semiconductor material that can produce semiconductor devices at 60 or 100 times more faster and higher voltage than traditional silicon material. And this is showing as a voltage and frequency product. So this is a capability that's going to try to get into more and more medium voltage application, and so this is why we think the time is coming for power electronics to go into the medium voltage application. So I have been basically pushing for this medium voltage power electronics transformation as well. But utility grid or the edge of the grid is a perfect application. And from a losses point of view, this device not only have a very high voltage, but their losses is very low if you compare with the silicon. Because of time, I don't have time to go into detail. You basically, every time you switch these devices, the amount of energy you have to dissipate or waste is almost zero for the turn off operation. It's not quite zero for turn on. The turn on is still substantial, okay? But in power electronics, we can apply zero voltage switching to get rid of this part of the losses as well. So suddenly this switch almost become ideal and with extremely high voltage. And this is one demonstration to show if you have soft switching versus no soft switching, we can get the efficiency close to 99% in a typical DC-DC converter. So this means we can build equipment which are very, very efficient. So efficient that they're close to the iron copper-based transformer, which is 99% or higher. But we're setting ROI to 97 or 98%, try to reach the traditional 100 years old transformer efficiency. See, here is an example. This is traditional, this is several prototypes developed in our group. Again, if you look at the underlying technology, material-driven technology is showing here. And this is, of course, 20 years in the making in terms of research material to devices, then to find it to application. And we're getting better and better performance in terms of power density, means we can make this smaller and smaller. And this is not, right now we are roughly here. This is the input voltage level, and this is the power density. But this is still at our laboratory level. I think there is a couple more times improvement in power density. This thing will be very small. So small, I think it's not totally impossible to have one per family at that level. And the efficiency is also getting higher and higher. This one shows that one of the latest one is about 98, but this one is only the DC-DC stage of this solid state transfer. So we're getting higher and higher efficiency for this technology as well. But this technology, if you just look at this is the voltage transformation from high voltage to low voltage, that is solid state transformer. But more important is to look at this is more than just a solid state transformer, it's a smart transformer as well. What do you mean by small transformer? Is they provide all this ancillary service to the utility grid, which is talking about they need in the smart grid era. For example, the power managing capability is absolutely what we need in the future grid to provide regulated voltage, to provide voltage, customized voltage profile. Remember the voltage frequency are all now decoupled between high voltage and low voltage. So this gives utility company or future new company a lot of possibility to do power management. And we can also limit the fault. This one behaves like a disconnect switch as well as a current limited devices. Then you can do the application. So these are short time constant applications. These are long time constant application. So the energy internet, of course, is targeting long time constant application because we're talking about selling energy, buying energy. But that's a typically long time constant application. But the underlying resiliency will be provided by this short time constant capability of the system. So there are a lot of this. I can show you a few examples. For example, voltage sag is a major reason losing a couple $100 billion every year for the utility industry or for the country as a whole. And of course, this one is a free product from this technology. We can design this to mitigate certain level of voltage sag. Here shows a 25% sag on the high voltage side, and on the low voltage side, of course, we don't see any sag. So this one has an economic value. So when you talk about the cost of a new technology, also need to look at what are the new benefit and capability the solution provide. And harmonic mitigation, of course, again, if you have a nonlinear load on the low voltage side, the harmonic will be blocked by this unit and not propagate back into the high voltage system. A lot of economic value. So don't just look at, so currently, for example, when we introduce this new technology, a typical question is cost reliability, right? So it's kind of difficult to directly take on that question. But you can look at this in this way, look at other benefit new technology can bring into the new grid. And then you can see the high voltage side is only 60 hertz, no harmonics. And another thing I want to show you here, this is actually an experimental result of this system sustained dead short circuit. And of course, traditional transformer, you have a dead short. The only thing that helps you is the high side breaker. But here, this system will achieve basically 20 microsecond level current limiting capability. So we can limit the current to absolutely the number we set. So this unit does not present as a low impedance unit to the overall system. And then you can take it off. So this is done already in the power electronics world. We understand very well how to do this. Of course, this is basically also the high end of the power electronics technology. We're talking about medium voltage power electronics solutions. But these are some capability. But another thing you need to do is how can you have all this system working together as a large resilient and system. So one additional area you need to look into is how to control all this equipment in the future. This is one SSD, this is another SSD that can provide support for 100% penetration. So typically when we talk about 100%, we always worry about voltage issue and we worry about frequency regulation. So I think traditionally you will use, we can inject VAR and we have to control the power flow to control the frequency. So in the future, this can be done very nicely because we have an individual addressable bus. Or the voltage is independent from every load to every load. So therefore, give you a degree of freedom to use that information to control the energy production on this local area. Basically, make a long story short, is we can introduce a communication link from the high voltage bus to the low voltage using a standard Joule characteristic, and then you can introduce basically a second Joule. The basic idea is this is done without communication. This is done at the physical layer. You can basically achieve a frequency regulation of the system. So this is basically one way you can think is to achieve short time constant control of the voltage and frequency to provide resiliency, to balance the power at any given time, and also to support the power flow when you go into islanding mode. And so this is, again, just the beginning of doing some research is how do you achieve autonomous control in all those intelligent equipment. They still work as a whole to keep the grid resilient with a lot of dynamic on the load and on the generation side. So then how about the energy router you mentioned so much? And the same capability where you have addressable voltage on this, each individual load center can be used to achieve a long time constant dispatch. This is just one way to do it. Another way is, of course, we will use a local area communication channel like wireless or Bluetooth to do it. And you basically can again, this is assume you will have some devices that understand its power flow based on this bus voltage change. example will be a storage device. Storage device. So by doing that, you can control the power flow here. But if you can, so this is needed for energy router application. Energy router is you guarantee next 50. If you have a contract with somebody you don't know, or with your labor to sell 10 kilowatt in the next hour, you're bound by that contract. You have to sell it, like today's large utility do. But large utility fulfill their contract with a lot of margin built into their system. So we have to have a lot of intelligent software which can predict your generation and your your own load demand, and can predict your excess energy, and you can dispatch. So this power flow capability can be achieved automatically in this SST-based energy router by using this capability. And it's basically showing here as an example is you can control constant power flow from a utility or from the high voltage side, a constant power flow. And if you can do that, this is your enabling capability to do economic dispatch. And if you can do economic, then of course the software will allow you to change and buying and selling by changing the profile. And then of course we can go into islanding because this capability, then of course you will not do this part. So what is the energy router? It basically, the major concept of energy router is ability to dispatch power from each localized area. This could be a building, could be a microgrid, could be individual homeowner. How do you do it? There are many ways, and this is one of the ways we are currently considering how to do it. I have a few more minutes. I think another technology we're developing is a smart breaker technology because of time. So this again is needed to have a more resilient grid where we can identify the fault, interrupt the fault, and reconfigure the system within a quarter cycle. If it's a DC system, we have to do even faster. A quarter cycle is already 10 times faster than today's electromechanical system. So we're developing another technology called smart breaker technology to achieve that. And we have some result to indicate that we now can achieve 1.5 millisecond breaker opening time using what we call the hybrid solution, where semiconductor and mechanical switch are simultaneously used. I still have some slides, but I think it's better to stop here and take some questions. The slides I haven't finished is really about the software. I think the basic idea is we need software infrastructure to support this, and we need software to be distributed also. Again, this is not absolutely agreed by everybody. Many major players think this will be just applied to today's cloud computing can do this. But we think there may be another need to develop more distributed architecture where the software is embedded into those equipment and allow peer-to-peer collaboration and application. So that's what I consider as the next major challenge is develop a software that's open standard based, and then you can write the application on top of the software. So with that, I think I would like to take a few questions. Thank you.
Thank you, Alex. This was a really great presentation.
Thanks for a great presentation. It's really fascinating. So this router, if I understand correctly, is bidirectional thing, so you can have both the drain and the source towards the high voltage.
This is
Like
this is bidirectional.
Right. Okay. Then how about what's your thinking that how will the, let's say, the commercial side of it be managed? So today we are paying for the energy for the utility company, but when we are behind this kind of a route, we will be both sellers and buyers. So in the architecture, how do you think this will be handled? The commercial side of it is there a clever out-of-the-box architecture for that?
Yes, our architecture does not assume you have to have generation. I think more importantly, like if you are purely a consumer of electricity, but you can still apply the software to your entity, which of course
That's one thing. You need a software to predict your day ahead energy need. Then you participate in this market, and you only need to buy.
Yeah, so I can be an island or I buy.
No, you cannot be island. If you are island, you cannot buy. So you have to be connected. You buy, but you don't buy from one utility. You buy from many utilities. You buy from many people. You can buy 1 megawatt, but megawatt can be break down into 10 pieces, where 1 megawatt is from your traditional utility company, the rest come from who you don't know. You don't have to know. But the software should automatically be able to clear. We actually have developed a software. We use a multi-agent, multi-person game theory to do the optimization, so you achieve the best economic benefit for everybody. So in that case, you don't have to have really generation, but if you have generation, it's just offset your ability. So the architecture support big and small player, but I think the key is everybody need to have the same infrastructure, otherwise they don't be able to talk to each other. So I think it should work. Yes.
Okay, who wants to be?
My name is Heli Angela. I come from utility company Prof. Thank you very much for the presentation, and especially the key enabling. Heard this before. One question about the status where we are now, and looking at the future, what you are calling there. Including, for example, in European Union, we have different market rules, regulation, and different kind of ancillary services in different countries. How can we come to this world, what you describe from the present situation?
Question. So that's why at least on the top, I need more policymaker and economists to participate in this research. I think, like I put it there, we can do in this one community at a time. We need to start from again, action is at the edge of the grid. So I think many times we talk about saying, oh, I need 1 million volt super strong intercontinental grid. That part I think will happen. It has its own life, whether that will happen or not. But I think there are a lot of community already has roof mount solar, electric vehicle. Can we start with the bottom-up approach? Behind the meter is fine. In front of the meter is, I think we need the utility and regulator in a local area to get involved. I think that's what I can think of at the moment. Go beyond the boundary, I think require definitely the government thing. But remember, this thing favors electricity flow in the local area. We're not talking about getting the bulk power from Germany transaction. I think the software will probably prohibit you to do that efficiently. Your cost will be higher if you move bulk power from other area across. It still happens. Maybe that can still, transmission ISO will still be there. They will still play part of those other things. I think utility company will basically provide whatever is missing. I think there is still a need to provide reliability and guarantee to the system, and they need to be compensated. So that's what I'm saying is any company provide ancillary service, keep the backbone voltage frequencies, that need to be part of the cost. And if I move my electricity, I have to pay you. So if I sell a kilowatt to my somebody, I think utility company will have a tax there.
So you think that the off-grid solutions will not be... So you think that off-grid will not be mainstream?
I think off-grid
Discussion is just like if you take your computer off internet, you're not going to get that benefit. I think I think if we purely talk about pure consumption point of view, but you could have a better economic benefit by connect to the grid. And we have to show that. If we couldn't show that, people will take more and more things off grid. I think that would be a sad thing. I think it's just totally against the internet thinking. So we need the grid. It's not advocating we don't need the grid. We just need a different kind of grid, basically.
Okay, retired professor in electrical engineering. I also have a general question concerning the transfer from the conventional energy system to this energy internet. So, where do you think that in this new sketch we will get the main savings in costs for national economy? Which parts of the system are relevant for savings?
Why is this one encourage more distributed generation, therefore encourage more of those on-site generation? So this will encourage user to be more willing to put storage, photovoltaic, EV, and other devices on there. That's the first thing it will help you to save. That's what we're doing today in microgrid, other pilot project, but it's in small scale. The second thing is overall efficiency, utilization. That part I think might be bigger one. It's overall energy efficiency. An example would be the software might decide it may be better for you to sell your electricity than you use it. So you could buy from other people. Depends on how the software work out. It's like so it will change people's pattern potentially for saving. So I think one is asset utilization and overall what I call the zero marginal price. Zero is not really zero; is getting lower and lower. Try to lower the floor because the business is lower the cost. If you look at all those business model, the price can only go lower because people are competing. I mean, of course, eventually the material and everything is still expensive, still going to go higher. But at the equal basis, it will drive down the cost. So I think there are two aspects we can see energy saving. So. Why? So I don't know. Yeah.
There were so many topics, and I'm sure we cannot continue this elaborate more here. I know that I guess that most of you are interested more about that. Alex, how long are you been here?
Next 2 months I'm here.
Okay, so that was that.
I'm
advertising that I know that there are a lot of company people here also. So if you want to have more lengthy elaborate discussion with things,
So please contact me. My name is Valery Vyatkin. I'm professor at the Department of Electrical Engineering and Automation. And I'm probably be hosting colleagues for the next 2 months. So he's located at Tulos building. You can contact him directly. It's easy to find his name by Google, or otherwise contact me.